I changed the title. So now it's Venus, Intrusive Magmatism Causes a Thin, Weak Lithosphere and Global Overturn Events. Next slide. Or can I change it? Okay. So we were running models of Venus a few years ago and published a paper in 2012. And in those papers, some of the models had a stagnant lid through the whole evolution. Some of them had episodic overturn caused by plastic yielding. And the ones with a stagnant lid through the whole overturn lost their, this is assuming that they have a sort of chondritic abundance of heat-producing elements. They basically lost their heat by massive magmatism. So we can see, for example, here, these are some of the models, temperature, composition. You see red is crust, so they form a crust. And you have partial melting. And here we have a heat budget. So black is heat input through radioactive heating. And blue is the total, no, red is the total heat output. And blue is the heat transport by magmatic heat pipe volcanism. So almost all of the heat in these models escapes by magmatic resurfacing. So magmatic heat pipe is the most important, and this leads to a cold crust and lithosphere because you're constantly assuming that all of the melt goes to the surface, produces crust, which is at the surface temperature, and so you keep piling this on top fast enough, you end up with a cold lithosphere. So it's similar to work that's been done on Io. And even with the back of the envelope calculation, you can calculate the amount of resurfacing that you get. It corresponds to about 300 kilometers of crust per billion years. And yes, it's about 10 times the amount that you get on Earth. So you just don't observe this. So you don't see such massive magmatism on the surface of Venus. So we didn't like these models so much. Another point here is that magmatism is very important in the thermal evolution of planets like this because it acts as a sort of thermostat on the internal temperature. And you can see that here. If you run a model without any magmatism, just purely thermal convection, the temperature rises because of radioactive heating. If you include magmatism, it more or less keeps the temperature constant throughout the whole evolution. So then there are models that have episodic overturn caused by plastic yielding, and these were, well, better in our opinion because you lose a lot of heat during these overturn events, and then you don't need to lose as much during these stagnant lid phases, and then you can end up with a relatively small amount of volcanism, more consistent with observations of Venus today. So these spikes correspond to overturn events. Here you can see a sort of animation of what one of these looks like. It nucleates in one place, so subduction nucleates in one place, and then it sort of spreads around the whole planet in about 100 million years. So episodic overturn due to plastic yielding, and this arguably better matches surface observations. So these models assume something like this, where all of the melt that's produced in the shallow mantle is instantaneously placed at the surface to make crust and cooled to the surface temperature. Your standard extrusive heat pipe magmatism, which has been argued, for example, by Moore and Webb to also be relevant to early Earth. And this leads to a cold, strong crust and lithosphere. But on Earth, most of the magmatism is not extrusive. It's intrusive. So maybe about 90% of the magmatism in Earth's crust and lithosphere is intrusive. And when you think about this, what we're doing is injecting hot magma into the crust and lithosphere, and this will have the effect of warming the lithosphere up, leading to a warm and therefore weak crust and lithosphere, if this is happening a lot. So the latest models that we're running include intrusive magmatism instead of extrusive magmatism, or some mixture of the two. And what we see in the next slide are some boring technical details. You can just look at the 2012 paper for this, but it's basically a compressible model that's supposed to sort of match physical properties of Venus as much as possible. So you have phase changes that depend on temperature, physical properties depend on depth, and so on, and temperature-dependent viscosity that's supposed to be realistic. And now what happens, this is a model without any plastic yielding, but what happens is you get episodic overturn events, such as the one illustrated here, purely by sort of runaway magmatism. intrusive magmatism weakening the lithosphere, allowing it to yield. And then they look similar to the ones in the plastic yielding case. You get, it starts in one place, and then once it's started, you get a lot of upwelling in the area that's gone down, and that causes more and more melt, which causes further weakening of the lithosphere. And then you can get a sort of global overturn event, facilitated purely by weakening of the lithosphere by intrusive magmatism. And this happens, you can see several pulses during the evolution of Venus, including one conveniently at about the right time in the past. So, I'll only show one model. What happens is that intrusive magmatism, even without plastic yielding, can cause a thin, weak crust and lithosphere, episodic overturn, and this model also seems to be consistent with surface observations. So then we could ask if there is any other sort of evidence for having magma in Venus's crust and lithosphere. And yes, I point to this paper by my colleague Taras Gurya, published this year, in which he has models in which he intrudes magma into the crust, and you get some sort of small-scale circulation, which produces features that look very much like coronae and novae. So this match to individual surface features on Venus is perhaps also evidence that you can have magma in the crust and it can be relatively weak. So the basic conclusion is that a thin, weak lithosphere possibly undergoing episodic global overturn may result from vigorous ongoing magmatic intrusion. How much time do I have? Okay, so I've got plenty of extra time, so I'll talk about the broader impacts now. And one point about these models is that magmatism actually can play a huge role in facilitating plate tectonics, both by the mechanism that I just described, like weakening caused by heating the lithosphere, and just the production of crust, oceanic or continental crust. So here we have two sets of models run by Diogo, my student, who's around here somewhere. In the top models, there's no magmatism, no production of crust, purely thermal models, and it stays as a stagnant lid the whole time. In the lower models, there's partial melting, which produces crust, and in these models, you see that there is episodic overturn of the lid. So simply having a laterally heterogeneous crust can focus the stresses or produce additional stresses that allow the lid to break, initiating subduction. And this is a regime diagram that he's come up with. On the right, so this is yield stress, and this is some reference viscosity. So at high yield stress, you get stagnant lid convection. At low yield stress, you get mobile lid convection. And simply switching on magmatism and the production of oceanic crust has moved the boundary between these different regimes upward in yield stress space by about a factor of 2. So now it becomes easier to have, in this case, episodic subduction by roughly a factor of 2. Now similarly, Tobias Rolf, we published this in 2011, had models in which you had yielding-based plate tectonics plus continents, which were compositionally distinct. And in these models also, you find that going from having no continents at all to just having some continents, makes it much easier to initiate subduction and plate tectonics. So it seems either, the important thing is this has to be laterally heterogeneous crust, of course, but it seems like either having continental lithosphere or crust and oceanic crust makes plate tectonics much easier to initiate. So I actually personally think that these models in which you just have purely thermal convection and you're trying to make plate tectonics are not really useful for making quantitative predictions for real planets. And then there's just some other models that I probably don't have time to talk about. But these are ones in which we start off with a completely molten planet, and as indicated by red is melt, I think, red is melt fraction. And then after a while, they settle down and you start getting crust produced, solid basalt, here it is. And then this very easily manages to subduct right from the beginning of planetary history. Okay, so that's the end. Thank you.
We have time for questions.
In the case when you added intrusive volcanism so that you could have a warm, weaker lid, when you got overturn, did it propagate all the way around the planet? Was it still a global feature?
Yeah, it did. You can see that back somewhere. Yeah, here. So this is a zoom in. So most of the time it's stagnant lid, as you see here. This is a zoom in of one overturn event, and yeah, you can see that it basically starts here, and then it propagates until the whole of the lithosphere has subducted.
So overall weakening of the lid is not able to halt the progress of the overturn, so that you just get a partial overturn in one place.
Not in these models, anyway.
Well, actually, I do have a question about this. So you have no plastic yielding, and so when this is overturning, is that the plastic yielding's turned off in this model?
In this particular model, yes.
So the overturn is just a density driven.
Yes. Well, even in the case where you have plastic yielding, it's also driven by density. But plastic yielding allows deformation to take place.